All right, today we're going to talk about section 2.2, general systems of linear equations. All right, so this is going to be a little bit more Gaussian elimination. There's an extra word or two that we're going to learn about Gauss-Jordan or elimination. And then we're also going to look at systems that don't have unique solutions. So all the ones we've done so far, when we worked and did the elimination, when we were done we had a matrix which was 1 on the diagonals and 0 elsewhere. You don't always get that. There's other situations that you get to when you do this elimination, and we need to see how to interpret those and what they mean. So we'll talk about that today. But the first thing I want to talk about today is part of the method of Gauss-Jordan elimination, and it's a word called pivoting. Okay, so to pivot a matrix around a non-zero entry, you first transform that entry to 1, and second, transform all other entries in that column to 0. Okay, so we'll do an example of this. So the problem will say pivot the matrix about the circled element. And let me draw the augmented matrix for this system here. 18, -6, 15, 5, -2, 4. And the entry they want us to pivot around is the -6. So we're supposed to pivot around the -6, and that means first we transform that -6 to 0, not by magic, but by one of the Gauss-Jordan elimination rules. And then after we've done that, then we do step 2. We use the Gauss-Jordan elimination rules to transform all other entries in that column to 0. So can someone tell me what the first step is in order to pivot this matrix? What do we do? Jack.
Multiply the first row by -1/6.
Okay, so we need to turn that -6 into 0, and the legal way to do that with Gauss-Jordan elimination is, as Jack said, to multiply that first row times -1/6. So it's going to be -1/6 times row 1, which is the same as dividing row 1 by -6. Right? So the 18 becomes a -3, the 6 becomes a 1, that was the whole reason, and then the 15 becomes a -15 over 6, which reduces to -7 halves. No, -5 halves. Okay, so, and then of course the second entry, the second column, we keep the same. Okay, so what we've done is step 1 of pivoting up here. We transformed the entry that we're pivoting around to a 1. Now we want to transform all other entries in that column to 0. Okay, so what's the step we take now to transform the other entry in that column, this -2, to 0? Can someone tell me what step we're going to do that? Sophia.
Multiply row 1 by 2 and then add.
Okay, so we're going to add to row 2 the product of row 1 and 2. That's what you said, right? Okay, great. So I'm going to write 2 times row 1 over here so I don't make any dumb mistakes. And then, here we go. The -3, 1, -5 halves stays. Now, 5 plus -6 is -1. 2 plus negative 2 is 0, of course. That's the point of what we're doing. And then 4 plus negative 5 is negative 1. Okay, so now we're done pivoting around that negative 6. We have that column to be 1 and zeros otherwise. Okay. So if there's a third row, then of course we probably have a third step of zeroing out whatever's in the other row's second column as well. Okay, questions? Is this okay? We're all right? Okay, so now let's take a look. I said there's going to be situations that don't get us down to that diagonal matrix with ones in the diagonal and zeros otherwise when we do the Gauss-Jordan elimination steps. So let's take a look at one of those and try to figure out what it means when things go slightly differently. So here's an example. This is a system of equations of x minus y plus z equals 3, x plus y minus z equals 5, and negative 2x plus 4y minus 4z equals 1. So there's my system of equations. I have 3 equations and 3 unknowns. So it becomes reasonable now to transform this into an augmented matrix and perform the Gauss-Jordan elimination to try to figure out how to solve this system. So let's do that. 1, negative 1, 1, 3, 1, 1, negative 1, 5, negative 2, 4, negative 4, 1. So there's my matrix. Okay, you know, it's not canonical how you start doing this. Let's pivot around this 1 here because it's already a 1, right? Like we want the top left entry to be 1 anyway, so we may as well pivot around this 1 here. And so now we're going to perform some steps here. We want to zero out both this element and this element, the 1 and the 2. So let's get rid of the 1 first. We're going to take row 2 plus negative 1 times row 1. Okay, or you could think about it as row 2 minus row 1. Okay, let's do that. So row 1 stays the same. Row 2, we subtract row 1. So 1 minus 1 is 0. 1 minus negative 1 is 2. Negative 1 minus 1 is negative 2. And 5 minus 3 is 2. Okay. And then let's keep that third row the same for now. All right, so we've gotten rid of the entry in the second row first column, which is what we want to do. Now we want to get rid of the entry in the third row first column to finish pivoting on the first column. So of course this step, we're getting rid of that red 2, negative 2, so it's going to be row 3 plus 2 times row 1. That will eliminate that negative 2. So I'm going to write 2 times row 1 over here, as is my custom, so I don't make any mistakes. Or, well, I mean, obviously I could still make mistakes. It's just a little less likely if I'm not multiplying by something, multiplying the whole equation by something in my head. Okay, so 1, negative 1, 1, 3, 0, 2, negative 2, 2, and then now we add this one and this one together. So we get 0, 2, negative 2, 7. Okay. So now I've finished pivoting around the first column. Right. Now we want to, okay, so the goal, right, is to get ones along the diagonal, right? The goal is to get these things to be 1 and everything else to be 0. So let's work on this entry here. We'll pivot on that 2 in the second column. So the first thing I'm going to do is multiply row 2 by 1/2. 1, negative 1, 1, 3, 0, 1, negative 1, 1, 0, 2, negative 2, 7. Okay, Now I would like to eliminate this 2 down here. To do that, I'm going to take row 3 plus negative 2 times row 2. And let's write negative 2 times row 2 over here. Negative 2, positive 2, and negative 2. Okay, so this that I've just written down is negative 2 times row 2. And I'm adding that to row 3. So the first 2 rows stay the same. Zero, 0, 5. Okay. Now see what happened here. When we tried to pivot on the second column, now look at that third row. That third row is 0, 0, 0, 5. Okay. Let's translate that back into an equation with x, y, and z, right? Because what we're doing is we're taking equations with x, y, and z in them, and we're forgetting about x, y, and z in order to do this algorithm and not write as many complicated things down. But now let's go back and see what system of equations we get from this. This would be a new system of equations which by Gauss-Jordan elimination is equivalent to the original one. We have x minus y plus z equals 3. We have y minus z equals 1. And we have 0 equals 5. Right? We have no x's, no y's, and no z's on the left-hand side for the third row. So if we wanted to write this down as an equation again, it's this system of equations. Can this system have a solution? Well, no, because this is something which is plainly false. 0 is not 5. When you do Gauss-Jordan elimination and you come up with an entire row of zeros, but then in the augmented part, we have a number that's not 0, then you get a statement which is false. 0 equals 5. So this means there are no solutions. There are no solutions to this equation, or this system of equations. Questions? Okay, so that's one thing that can go wrong and prevent us from getting that ones on the diagonal that we desire, is that one of the rows turns to all zeros, but the augmented part doesn't have a 0 there, and then when we reinterpret that as a system of equations, like we did here, we get something which is patently false. 0 is not equal to 5. So then we know the system has no solutions. Now let's do another example, which we get a different situation. Okay. 2x plus 2y plus 4z equals 8. X minus y plus 2z equals 2, and negative x plus 5y minus 2z equals 2. Okay, so this is again 3 unknowns, 3 equations. So from the beginning, this appears to be similar to what we had in the previous one. And of course, to see what happens, we have to start doing this Gauss-Jordan elimination. So let's turn it into matrix form. 2, 2, 4, 8, 1, negative 1, 2, 2, negative 1, 5, negative 2, 2. All right, so there's our augmented matrix, which stands for this system of equations. And as per our usual custom, we'll pivot around this 2. So that means the first step is to multiply the first equation by 1/2. All right. So we've got the 1 that we want, and now we can take the next step would be, and I'm working a little more compactly than I have before. So I'm going to take row 3 plus row 1. Right? I want to get rid of this negative 1. So 1, 1, 2, 4. 1, negative 1, 2, 2. Now we're adding the 2 rows here. We get 0, 6, 0, 6. Okay. Now let's get rid of row 2's leading 1. So it's going to be row 2 minus row 1. Row 1 stays the same. Now row 2, we're subtracting row 1. So 1 minus 1 is 0. Negative 1 minus 1 is negative 2. 2 minus 2 is 0. And 2 minus 4 is negative 2. Okay. Now, this is the first sign that something's a little bit weird, right? If we try to turn both of those rows into, well, let's pick one of them and pivot around it, right? So let's pivot around this negative 2. So we're going to take negative 1/2 times row 2. 1, 1, 2, 4, 0, 1, 0, 1, 0, 6, 0, 6. Okay, let's first eliminate this one because we're pivoting around that second column. So this is going to be row 1 minus row 2. 1, 0, 2, 3, 0, 1, 0, 1, 0, 6, 0, 6. So I took row 1 minus row 2. Now we wish to eliminate this 6. And to do that, we're going to take row 3 minus 6 row 1. 1, 0, 2, 3, 0, 1, 0, 1, 0, 0, 0, 0. Okay. Now we've got zeros in an entire row again. Right? Remember the last one, when we got to the final step, we had 0, 0, 0, 5. This guy right here. Now, however, we have 0, 0, 0, 0. This is fine. This is not something that's untrue. When you change this into an equation involving x, y, and z, this is 0 equals 0. That's a true statement. It's not a false statement. So this doesn't blow up, but now let's look at what's going on here. Let's rewrite this as a system of equations. This is x minus 2z equals 3. This is y equals 1. The second equation is y equals 1. And the third equation doesn't exist anymore. 0 equals 0. Right? That's not adding any information. Okay, we already knew 0 was 0. So what's going on here? Well, here, when you get this row of zeros, this is a telltale sign that there are many solutions. There are many solutions to this system. Now, we do know that all solutions are going to have y equals 1. Okay, so all solutions have y equals 1, but then otherwise, we just have a relationship between x and z here. So we can say, rewrite that first equation as x is equal to 3 plus 2z and y is equal to 1. So we just rewrote this in this way. This is saying, what does this say? This says that y must be 1, z can be anything, and x must be 3 plus 2z. Okay, I'll show you how you would write some specific solutions in a moment. But that's what we've learned from doing this Gauss-Jordan elimination, is that y has to be 1, z can be anything, and x is equal to 3 plus 2z. Did I do something? Oh, I'm sorry. Okay. This should have been a plus, right? This is a positive 2. And so some of these should turn into minuses. Okay, I messed up in copying down that equation. So for instance, here is a set of numbers that solves this. I said y has to be 1, z can be anything, so we'll let z be 0. And now x is equal to 3 minus 2 times 0. That is 3. So x equals 3, y equals 1, and z equals 0 should solve this. But so should if we choose y to be 1 and z to be 2. This is 3 minus 2 times z, which is 2, 3 minus 4, which is negative 1. So x equals negative 1, y equals 1, and z equals 2 is also a solution. In fact, there's infinitely many solutions because we can choose z to be anything, and once we choose z's solution, that forces us to pick a specific x. Okay, so in a minute or two, I'll talk about the rules, like how do you know when you have 0 solutions, how do you know when you have infinitely many solutions, but let's talk about what's going on here geometrically. In 2 dimensions, we have 2 equations that are needed to solve these things, and those 2 equations are 2 lines. So if you're in 2 dimensions, there's 2 equations, and those are 2 lines in a plane. How can they intersect? Well, 2 lines in a plane can intersect like this. They can be parallel, or they can be the same doubled up line. That's the only way for 2 lines to lie in the plane. The first one is when you have a unique solution. The second one is no solution. And the third one is infinitely many solutions. That's geometrically what's going on with any 2 by 2 system. 2 equations and 2 unknowns. 2 linear equations, 2 unknowns. The picture will look something like that, one of those 3 options. You either have 2 lines which cross in a unique point, you have 2 lines which never cross, or you have 2 lines which are simultaneously the same thing. And so there's many, many solutions. Anything on the line is a solution. Now let's think about what's going on with 3 dimensions. 3 dimensions leads to 3 equations. And these equations are actually planes. A linear equation in 3 variables, like 3x plus y plus 2z equals 7, is actually the equation of a plane in 3-dimensional space, an infinite flat plane. And there's different ways for planes to intersect. Okay? They can intersect like this. Here's 3 planes. And they can intersect at one point. Okay, 3 planes can intersect at one point. And that is when we have a unique solution. Another way we can have 3 planes is if they're all parallel. Where we'd have no solution. We can actually have no solution in different ways. If we have 2 parallel planes, and then a third one that intersects both of them, right? This would be no solution too, because there's nothing that's on all 3 of those planes, right? Because 2 of them never touch. So there's no point that's on all 3 of them. So that's a possibility. There's also the possibility that you get infinitely many solutions. This one's probably the hardest one to draw. There's a nice picture in the textbook, but I'll do my level best here. This would be like, if you looked on that from above, you'd see an asterisk or a star. They're all coming together, but there's this line here is actually all of the solutions. So this is infinitely many. There's many things which are on all 3 planes. That's the geometry behind what's going on here, right? And in a class called linear algebra that math majors take and engineers take and stuff, you learn a little bit more about this geometry and what's happening here. But I wanted to show you what's going on. In 2 dimensions, you're used to the fact that lines can cross in 3 different ways. But in 3 dimensions, planes can cross in a variety of different ways. Now, how do you know which situation you are in? And that is covered in these rules. Okay, so rules when finishing Gauss-Jordan elimination. Okay, the first situation is if you get 1s on the diagonal and 0s otherwise, that leads to 1 unique solution. And everything you did for homework today had 1 unique solution. Okay, because they were specifically made that way in that section so as to not introduce these more ambiguous situations while you're just learning the process. So if you get down to where you have 1 0 0 0 1 0 0 0 1 and then stuff over here, that's 1 solution. The second possibility is if you get any row of 0 0 0 and then A, where A is not 0, then you have no solutions. Because that row means 0 equals A, and 0 equals A is not true if A is not 0. So you have an equation which is an impossibility in your system of equations, and so that means there can be no solutions. Okay. And it doesn't have to be the bottom row, it can be some other row. If you get any row that has all zeros and then a non-zero thing to the right of the bar in the augmented matrix, then you have no solutions. And 3, if you get a row of just zeros and even a 0 after the bar, then you have infinitely many solutions. All right. Now, we don't have a lot of time, so I'm just going to write down the homework problems. This is section 2.2 in the textbook. Problems 18, 22, 24, 26, 28, 30, and 32. Okay, so just 7 problems for you. This will be due Monday. And as I said, Monday we will be doing review for the first exam, which comes on Wednesday. All right, folks, have a good weekend.